you'll want to take your seat if you're here for our Q&A with Tim today. We're going to go ahead and get started. You guys are fine there, but there's also seats in the front row if you'd like. All right. Well, thank you all so much for joining our session today. Very honored to have Tim come down from Vancouver and do this Q&A with us today. Here at the NFT Museum, we really focus on education as a core part of our mission. And for us, education just doesn't have to be specifically about art, but we also just want to be able to be a forum to bring together the greater Web3 community as well. So very excited for you to hear more about Ethereum's transition and roadmap from someone who is intimately focused on this day to day. So please welcome Tim Beiko.
First, thank you so much for having me. This is a really cool space. I'm Tim Beiko. I work at the Ethereum Foundation. There, I basically work on the transition from proof of work to proof of stake now. So that's what I'll be talking about today. I have got a presentation and some room for questions at the end, but if you all have questions during, feel free to interrupt. There's plenty of time, and I just want to make sure that people don't get lost. And I guess there's a few things I'm going to walk through. First, just to kind of lay the groundwork, explaining what is proof of work and what's proof of stake, and why and how do we use them on blockchains, and what are the properties that these things give us. And once that's kind of explained, I'll kind of walk through from Ethereum's perspective how the design of proof of stake has changed over time, and why you've been hearing from proof of stake for the past 5 years. What have we been doing at that time? After that, I'll kind of walk through what we call the merge, which is this idea of moving Ethereum, which currently is under proof of work, to proof of stake. How does that work conceptually? And then walk you through kind of where we're at in this process of the transition. I have a couple misconceptions about it at the end, and then some time for Q&A. But again, if you have questions throughout, just raise your hand and we can pause. Okay, so I guess the first thing to unpack about proof of work and proof of stake is there are actually terms that we use to describe two sorts of mechanisms that are useful to blockchains. And these are consensus mechanisms and anti-Sybil mechanisms. And a lot of the confusion about what they do, how they work, stems from conflating those two things and not being able to address what are the base layer properties that we want. And so on the consensus mechanism side, this is basically a way for a blockchain to answer how do we agree on what the current block at the chain is and the history leading up to here. And if you look at Ethereum today, we use something called GHOST, which stands for greedy, heaviest, observed subtree. But basically what this means is you look at all of the proof of work branches that you have, and you take the one with the most difficulty on it, so the most hashing power. And proof of stake works kind of the same way. So in proof of stake, instead of having miners that contribute hashing power, which is seen as difficulty by the protocol, we have validators who put up collateral or a stake in Ether, and that contributes economic weight. And so if you have a bunch of conflicting histories, you discriminate between them, between which one has the biggest economic weight between them. And so this is kind of half of what you get from it. But then the other pretty important part thing that these mechanisms do is they give us Sybil resistance. And Sybil resistance is basically this idea that on a blockchain there's no identity. So there's no easy way to assign the rights to someone to create a new block. Right? If this were a country or a government, you could say, everybody with a passport or an ID takes their turn to produce a block. But because we don't have this concept, right? Anyone can create an infinite number of Ethereum addresses for free, basically. You need a way to say okay, how do we do this without getting totally spammed and without having a central third party that dictates who this is? And the way we do this on blockchains is just by forcing people to put up economic resources in a sort of lottery so that their chance of producing a block is proportional to how much economic resources they've committed. And then again, in proof of work, this is the amount of energy or hardware that you put up, and in proof of stake, it's literally your stake. And just to touch on this Sybil resistance point, because emphasize. If you didn't have this, what it would look like is, well, if anyone can propose a block anytime on Ethereum, regardless of proof of work or proof of stake, the nodes on the network would be completely spammed because they would just get millions of potential blocks coming in at a time, and they can't figure out, okay, which one should I build on? So it helps you kind of discriminate between this. And then again, we don't want to trust in third parties, so we can't create just like a list of like official block proposers that we add to, because there's no one to manage this. And the last thing is also we would like, ideally, for both proof of work and proof of stake, to be scalable to a large set of potential participants. So it's not restricted to, just like very rich or very large entities. Okay. So if we look at like proof of work, which is what Ethereum uses today, and kind of based on what we just talked about, like why is proof of work a good mechanism for us to use? So first, if you look at this idea of like, okay, we need to figure out how to assign this rights to produce a block. In proof of work, it's quite easy because you just have these miners competing all the time to do it, and because this is like an expensive competition, the protocol can issue them new units of the currency, Ether, to reward them for this. And the other pretty neat thing about proof of work is that it relies pretty heavily on cryptography, where it's really hard for a specific miner to find a solution, but it's very easy for anyone observing the chain to know that that solution was valid. And we'll go into that a bit more after. But this is why you don't need to trust a third party, because you can just look at a solution by a miner and know that, like, mathematically, the output from this is what you would expect. And then there's no kind of barrier to entry in proof of work, because literally anyone can turn on a miner and try to mine a block. And again, we'll dive into like the specifics of how this works later. There's no guarantee that you actually find a block and are profitable, but there's no explicit barrier to entry in the protocol. You can choose to start a miner today, and there's literally one running right there. And yeah, so to dive into like how this works a bit more, when we have these miners mine, basically the things that they do is they're searching a random space for an input to a function that's constrained within a specific domain. And this sounds like a mouthful, and I have a little video after that explains it more visually, but a lot of times there's like this perception that like miners are doing like hard work or solving hard cryptographic puzzles, and it's hard in the way that like winning the lottery is hard. Like they're solving a problem which has a low probability of succeeding, but it's not hard in the way that like it's an impossible problem to solve. It's just like solving a trivial problem trillions of times over and over, and then if you're lucky, you kind of win the block. And again, like we talked about, because it's hard, it kind of limits the amount of potential solutions that come in. But once a potential solution comes in, that you have like a proof of work block coming in, then any node on the network can trivially verify whether or not it's a valid block. And then what we do to make this scalable is basically, as more people want to mine on Ethereum, we just raise the difficulty to mine a block, so we kind of make this lottery harder to win. And then if not enough people are mining, then we just make the lottery easier, and this kind of modulates how much people are mining on Ethereum. Okay, and now I have a little video that shows you like what exactly happens when you're mining. So this uses SHA-256, which is a different function, but basically the same concept. Okay. And you can see every time there's like a new input that comes in, it automatically generates like a new output, right? And this is like, it happens like instantly. And so what miners do is they take like the list of potential transactions in the block, and then they add a random value, to +1, +2, +3, trillions of time, and what they're trying to find is a solution here that starts with like a specific number of zeros. And as you can see, I've done it like 10, 20 times here, didn't find anything valid, but this is really what's happening, is they're running like this super simple hashing function, but running it super often so that they reach kind of a solution that randomly will have enough zeros to satisfy the current difficulty. And yeah, so like why do miners actually do this on Ethereum, and ideally why they do it honestly? So first, we talked about this earlier. When they produce a new block that is valid, they get new units of Ether, and that acts like an incentive. But then the other part that's really neat is because anyone can verify that a block is valid, it creates an incentive for them them to actually mine on a valid block as well, rather than like start their own Ethereum chain. Because, or to kind of have an invalid block which gives themselves an infinite amount of ether. Because they know that when they produce a block, everybody on the network is going to be checking it. So if they did something like, increase their balance by 1 million, everyone would see it and they would just reject that, and the next miner would just not build on that block. And then similarly, if mining becomes kind of too profitable, what happens is like the protocol just makes it harder, and so over time it becomes less profitable, and if it's too hard at a certain time, the protocol makes it easier, so we kind of reach an equilibrium in terms of miner on the network. Okay, so that was proof of work. I guess I'll pause here. Does this generally make sense? Okay, awesome. Okay, so how does this compare to proof of stake? We want to get like these same properties where we're giving out the right to produce a new block, don't have to trust a third party, and ideally want it to scale. And so the thing that's different from proof of stake is instead of having this randomness that's kind of generated by this process of looking for a solution to a problem by mining, we just have a random number generator in the protocol that shuffles stakers periodically. So basically, there's some randomness value in the protocol. It takes the entire list of potential stakers, shuffles them around, and then tells them, okay, this is who's going to produce the next block and block after that, and so on. And so stakers all have kind of the same amount of ether, validators on the network have like the same amount of ether per slot. So the amount of like validators that you run is basically the number of like tickets that you have in the log, right? Similarly to how in mining, if you have more of the miners on the network, you have a higher chance of producing the next one. So we just shuffle them in protocol. And the difference though is, unlike proof of work, there's not like a cryptographic puzzle that they have to generate and then others verify. But what they do is that they do put together a correct block, and other validators on the network need to vote on it. And if they vote on it, they'll get a reward if other people think that they voted the right way, and they'll get penalized if other people disagree with that. So for example, if a validator puts out like a valid block, and everybody kind of says it's valid, and then you say it's invalid, you'll get penalized for that. And vice versa, if a validator puts out an invalid block, everybody says it's invalid, you say it's valid, you'll also get penalized. So we're able to just have this verification happen in protocol, and because all the validators have put up collateral in the protocol, we can reward and penalize them based on what the rest of the network thinks is the right outcome. And then, kind of similarly to how in mining, we like make the mining function harder as more people want to mine, what we do instead with staking is we simply reduce the potential returns to validators. So, you can think of like the validated rewards as some sort of like interest that people get if they perform the right duties, and we just like reduce the amount of interest as more people come in to again find kind of an equilibrium. Oh, and so why would like validators come on Ethereum and stake and do so honestly? Well, there's basically three things. So one, there's rewards, just like on proof of work. If they do the right thing, they get rewarded when they create a block with new ether issuance. Like we just talked about, there's also penalties. So if either if they don't basically vote on anything when they're supposed to, we'll penalize them. So if your validator is offline, it just gets a penalty kind of proportional to how many other people are offline. And the reason for that is that we need validators to move the protocol forward, because if no one's agreeing on the current state, then the chain stops. And the more validators are offline, the worse the problem it is for Ethereum, so we kind of ramp up that penalty. And this has this kind of neat property that it makes it easier for like individuals to be validators than like really big entities, because if you just run like one validator in your basement and you go offline, you'll have a pretty small penalty. But if you're running like a third of the network and you go offline, you get like an exponentially larger penalty. And this is kind of advantageous for smaller people, because the network kind of doesn't care if just one validator was offline, but if a large percentage of it was, that's problematic, so we want to penalize more harshly. And then finally, there's kind of an even harsher penalty than that, which we call slashing on Ethereum, where if you're a validator and you kind of attest to two different histories, or histories that contradict each other, that's really bad, because it kind of tells the blockchain like there's two potential histories and you've like deadlock between them. So what we do then is we take a larger part of your collateral away and we kick you out of the validators. So this is considered like really bad behavior. And if you're like a user running, the software, this like can't happen by just running the vanilla software. It can happen either just like through a malicious attacker who wants to kind of mess with the network, or through like a bunch of complicated DevOps settings that we've seen some larger validators do at scale. But this is really kind of the worst penalty we have because the kind of fault that validators do there is really bad from a protocol security perspective. So, I guess at a high level, just to like compare the work for stake, the systems that like give us similar properties in terms of what they achieve for the blockchain, but they take kind of a different path to do it. So the miners don't invest capital in the form of hardware and electricity, and the amount of hash rate that they have relative to the rest of the network is kind of their likelihood of producing a block. And then validators, they'll lock actual capital, which is Ether, and then they get a reward on that if they perform well, they get a loss on that if they perform badly, and similarly their share of the total stake is kind of the likelihood of producing a block. What we do on proof of work, if more people want to mine, is we just make it harder to mine a block, so we increase the amount of hashing required to mine a block, and we leave the reward constant. And we do sort of the opposite on proof of stake, where because blocks are trivial to create, we'll just decrease the rewards as more people come in to, again, kind of reach an equilibrium spot. And this last point, miners, they're incentivized to mine an honest block because they know everybody else is verifying it. So if they mine a dishonest block, they know that other people will just ignore them. We call this orphaning in blockchain terms. But there's no like direct penalty. It's kind of like an opportunity cost penalty. Like they're not making the reward that they could have made, but you can't really take anything from them. Whereas on proof of stake, we can very explicitly, take something away from the validator if they are either offline or you propose them invalid. Does this make sense so far?
Me too. Yeah. Is there possibilities where maybe a large validator, a large stake in UPOS, is it possible that through malicious code they could potentially change the path?
So what they can do, they can basically, there's different levels of stake. If you have more than a third of the total stake in a validator, they can basically choose to stop the chain from progressing. And this has a very high cost to them because as they're doing that, everybody gets a penalty because from the network's perspective, it's like if these people were offline. So it's a pretty high capital cost to do that. If they have more than 2/3 of the stake, what they can do is they can make a commitment in the history of something that may be invalid. And then what happens, like we were talking about before, there's like these slashings. What happens is that if they make this type of commitment that like people, say there are 2/3 of validators, they print themselves a million Ether. What will happen is then the minority of the other validators, they would see that as invalid, and in their view of the blockchain, they would kind of take away that, they would punish those validators, and then over time, as those validators would be like exited from the validator set because we kicked them out, this can take a couple weeks. Then this chain, they go from having 1/3 to 2/3 to like over time taking them out, and there'll be a point where that like 1/3 of honest stake actually represents 2/3 of the stake that's left once you've kicked out more than half of the attacker's validators. And then the chain will kind of keep finalizing again on the right side again. So the validator will have like the attacker will have like disrupted Ethereum for like on the order of weeks, and that's obviously not great. They will basically burn all of their money doing this, and the network can kind of self-heal in a way there. So it's and then similarly in Bitcoin, if you have more than like 51% of the hash power, or on Ethereum, like in proof of work, there's also a bunch of things you can do, like you can't censor the chain, you can't stop it from progressing, and so one way to think about it is like, at about like 1/3 of the stake on proof of stake, you start having some attacks that like you can do to disrupt the system, and that's the level that like we try to like keep below. On proof of work, at half of the stake, there's some. At 1/3, there's like some things you can do to just like economically disadvantage others. So if you get to like 1/3 of the hash rate on proof of work, you can like disadvantage others so that you quickly get to like 51% and be able to mess with it. But generally, like, yeah, those are the thresholds where like, you know, people can attack these systems, and then there would need to be, like, there'll either be like many weeks of instability, or like there needs to be a solution coordinated outside. And to put this in perspective, you know, this is on the order of like tens of billions of dollars for both cases. So it's like you need to have a willing attacker that's willing to like burn this amount of capital, which is not impossible, but it's like you can think of this as like the level of security that you get when you're making like a transaction on Ethereum today. It's like, you know, if you're not transacting in one shot on the order of like billions of dollars, there's no like incentive for someone to like disrupt that. But if you are, like, you know, if I was sending like a $20 billion transaction on Ethereum, that's probably something you want to consider. Yeah. Does that make sense?
Yeah, thank you.
So just to build on that, how would you, do you have ways of knowing if you're getting close to a third of validators potentially colluding? What ways would you have of doing surveillance on that?
There's ways that protocol can know, and there's ways that you can hide within the protocol for sure. Like, I mean, you know, imagine like Coinbase has validators, for example, right? Like, and you can see how much is deposited there, and like what's the share of that over the total. But they could also, you know, you could imagine behind the scene, like, I don't know, Coinbase and like Binance colluding, right? And they each have like 18%, then that's enough. So there's definitely like both in proof of work today and proof of stake, like a single-digit number of actors who like control more than like those minimum thresholds across Bitcoin and Ethereum. I think that the big, and we'll get to this in like proof of work versus proof of stake after. The big difference with proof of stake is you can identify those validators in protocol, and you can like either have the protocol automatically like punish them if they collude in ways that's detectable. If there's ways that's not detectable, you can have people just agree, you know, to have a fork, like a change to the protocol, and remove those misbehaving validators. And that's like a very contentious thing. And similarly on proof of work, you can agree to remove like a set of miners by changing the mining algorithm. And it's like a bit more surgical on proof of stake because you can identify just like the subset of capital you want to affect. Whereas on mining, you need to change the entire algorithm. So like, yeah, you can see, and there's like clearly some level today where like there are scenarios where this collusion would be possible across proof of work or proof of stake. And yeah, if it happened, then you would need to coordinate something outside the protocol to resolve it. Yeah. Any other questions? Okay. Yeah, those are really good questions. Yeah, so I guess, you know, some of the reasons, like, you know, why are we moving to proof of stake on Ethereum? And we've been just talking about this, but like this idea that we can identify and punish like stakers who misbehave very surgically through like, you know, their single kind of validator on the network. That's a really useful property for security. And you can even imagine like the protocol can't really distinguish between like malice and incompetence, right? It kind of is the same to Ethereum. And so you can imagine if you're running like 2 validators in your home and like you spill your coffee on one of them and like, you know, break it, the protocol can actually like figure out that one is offline and like, you know, penalize that one, but not the other one. And this is like a really valuable property that we get in proof of stake, whereas in proof of work, we don't know anything about the miners. There's no like, there's no tie between like their footprint on the protocol and their footprint in the real world. So we can't like granularly apply penalties like that. And because we can do that, one main property of proof of stake is also, it's just like, it costs less to the network. Because not only are we like applying rewards and kind of applying enough rewards to force everyone to collaborate and be on the same chain, we can also apply penalties that people defect and go against. So that means the rewards can be lower because it's kind of, you have a carrot and a stick rather than just a carrot. And in practice, what this means for Ethereum is the proof of stake issuance is about 10 times lower than the proof of work issuance. Another neat property also proof of stake is there's less economies of scale for block producers. So in proof of work, because there's really high fixed costs in terms of energy and hardware, you can imagine that like if you're starting an industrial mining facility, you have better rates on those things than if you're just running a miner at home. Whereas in proof of stake, every incremental capital deposited gets the same return. So whether you have like 10 validators, 100, there's no like big economies of scale. Obviously, you'll make more money, but you'll make more money in kind of a linear way rather than like an exponential way. And then obviously the big one that everyone talks about is there's no environmental impact. So like proof of work is literally a system that takes like real world resources and scales the demand for them as there's more demand for blockchain. So we need more electricity, more machines, that's why people want to use Ethereum or Bitcoin. And proof of stake, we literally just use like money that's running on the blockchain. So we don't have this demand to like run really performant computers and grow that number, which is where basically all the environmental impact of blockchain is. And yeah, I'll play devil's advocate a bit here and kind of talk about like, what are like some of the disadvantages and trade-offs of proof of stake and why Ethereum is like okay doing those. But the first is like the increased protocol complexity. So proof of work is really simple and from a protocol perspective because you literally just get like solutions to puzzles that are trivial to verify. And if they're right, you have them in the chain. If they're wrong, you can take them out. Proof of stake has like this whole other kind of system which you need to have all these validators vote, you need to shuffle them, you need to like change how much you're paying them and whatnot. So there's just like more complexity in that protocol. And so what Ethereum did to like address this is first like a proof of stake chain is like separate from the main Ethereum chain. We launched it separately, kind of ran it for a year, and wanted to make sure that it worked at scale with billions of dollars in it before we brought it in the security chain. But that's definitely one thing that you get there. Other thing is this idea called weak subjectivity. So in proof of work, if I give you like a block, like if I give you the latest Ethereum block today, you can like trace back mathematically, offline without the need for like anyone on the network, that history all the way back to the first Bitcoin block or Ethereum. In proof of stake, there's some time vectors where like if someone's a validator and then they quit being a validator, they could like sell their keys that they use to create blocks, and somebody could just create like a fake history of those blocks. And again, this is like not necessarily the most practical thing to do, but it is quite possible. And so this means that if you're like completely offline, you can't connect to the internet, and I give you like two conflicting histories of Ethereum that are more than like a few months old, there's no way for you to like figure out which one is the right one without asking the Ethereum protocol. Whereas on proof of work, you get that property. And there's no way around this, so Ethereum's solution is basically, we accept this. And the reason why is that most of like the contentious part of blockchain history is the very recent one. Because blockchains like they have like these permissionless block producers, it means that like short term there's sometimes like some we call those reorgs, but just like the history changes a little bit. But over time, this basically becomes less and less likely in a pretty like exponential fashion. So like, and to make this concrete, it's like if I ask you, what's the latest Ethereum block right now, we might disagree. There might be like 3 potential ones, and then that fork kind of gets resolved. But if I ask you like the Ethereum block from like a year ago, everyone would agree to like what that block is. Or Ethereum basically thinks that enough people would agree such that this is impractical. But there is like this theoretical kind of stain if you want. Another thing also that's a bit inconvenient for the sake is like I mentioned earlier, we need to shuffle these validators to have them produce blocks. And because validators, need to know that they're going to produce a block, we need to tell them a bit in advance. So usually, like we know about 6 to 12 minutes in advance who's going to produce like the next 6 to 12 minutes worth of blocks. And that creates risk where you can imagine if those validators reveal their IP, then people could decide to like attack these specific IP addresses. And basically, there's 2 like solutions to that Ethereum is working on. One is like SSLE, we call it secret single leader election. It's just a very fancy cryptography that we're working on to like obfuscate this whole thing. It's not live today. In practice, though, there are like some DevOps things that you can do to just secure your validator against this, which is what people run. But it does like the fact that you know who it is early leaks a bit more information, which kind of creates a bit more overhead if you want to protect against it. And then the last one, so I kind of marked this one out because the last one is like a proof of stake thing, which Ethereum does not have, but it gets confused a lot. A lot of proof of stake chains have like a very small number of validators, on the order of like 10 to maybe 1,000, but in practice it's more like 10 to 100. And Ethereum does not have this. We have about 400,000 validators now, so a couple of orders of magnitude more. And this is why it took so long to ship the proof of stake thing, because there was bunch of research that went into making that possible. But it is like one of the challenges of like most proof of stake blockchains is just you can't have like a really large number of validators. Like on proof of work, you can have pretty much infinite number of miners. Okay, so I'll kind of walk through now like how we got to the current design we have for proof of stake. So in 2017, Vitalik and a few other people proposed the first paper about how the proof of stake consensus mechanism would work, called Casper, and that would have on archive then. And then people took that and then started prototyping it. And the first version of this, because this was kind of new technology, we figured, well, we might not want to go like all in with proof of stake if it's still quite new. So the first version was actually like a hybrid, which would use like proof of work for some blocks, proof of stake for some blocks. And the idea was that like maybe over time you deprecate proof of work, but if proof of stake is broken, at least you can fall back on proof of work, and we know it's a bit more trusted. So we had this idea in around like 2018, which got prototyped and almost got launched. And this is when people say like proof of stake, took forever. In summer of 2018, basically we decided to scrap that whole thing and start with like a new roadmap. And this is what we have today. And the reason is there was, in parallel to this proof of stake work, a lot of work happening on how we scale Ethereum. And both were being done pretty independently and kind of as extensions to the current protocol and inheriting a lot of like the technical trade-offs that Ethereum had taken under proof of work, even though they weren't super relevant for both the scaling and proof of stake roadmap. So in 2018, people got together and decided, well, what would it look like if we just like redesigned proof of stake from scratch, separate from the current Ethereum chain, and instead, like didn't have any of these assumptions in the design. And it actually would look much better, so people decided to do that. And then it took like a year basically to get that specification done. So in like summer 2019, there was like an interop event with a bunch of researchers and developers, and that's roughly when we hit like frozen specification for what is the current proof of stake chain. And then, everything in Ethereum takes longer than we expect. So from that time in 2019, it basically took over another year so that we had something that we considered like worth going live. And to kind of put this in perspective, like some of the changes we made in them reduced, for example, the amount of stake that you need to be a validator from 1,500 ETH to 32. So that's about like 50x lower. And this is why we can get a much larger number of validators on the network. Another thing that we did is it does kind of have these validators run the proof of stake algorithm, but also it just lays the architecture in a way that we can then add more duties on them, and that will help scale Ethereum after, and we'll talk about that. So it was a lot of work and a lot of obviously like iterating on the design, but it got us something that was cleaner, that was more accessible, and that eventually went live. So in December 2020, the proof of stake launched, the proof of stake chain sort of launched. And like I mentioned earlier, this was launched separately to like the current Ethereum chain with all of the applications, because at that point there was a ton of activity on Ethereum already, and we didn't want to just move to a completely new system. And then about 6 months after that, so in May of last year, the proof of stake chain had been running quite well. There hadn't been any major issues with it. I think at the time it was something like $20–30 billion securing it. No one had hacked that, taken the money, so things were looking good. And we started to feel confident that, okay, this is solid enough that we can now use it and start thinking about how do we transition all of Ethereum to use this rather than proof of work. And this is what we call the merge. So basically the merge is this idea that we take the Ethereum chain right now that's running proof of work and all the applications, and the proof of stake chain right now that has all these validators but doesn't run applications, and merge them together such that we don't need to rely on proof of work anymore. And then here it's also worth kind of talking through why we ended up with this design, and I don't know if some of you have been following Ethereum for like a few years, you might like have heard about this Phase 2.0 roadmap, which like had this picture that was very popular a few years ago. But if not, this might be the most confusing part of the talk, and I apologize in advance. I'll try to keep it simple. I think like in the summer 2019 workshop, the idea that we had to like scale Ethereum was a three-phase roadmap, which starts with phase 0 because the programmers and start at 0. And the first version was like, okay, we launched this proof of stake chain, which is what we actually did in December 2020. And then we wanted to instead move all of the applications to that. And instead of having just one Ethereum chain kind of running all the applications, we want to have a bunch of them running in parallel so that we just get more scalability. And this idea was called sharding. And then we realized that, like, well, it's quite hard to like manage a bunch of applications running all in parallel. So the idea was to instead just start with data sharding, meaning that they wouldn't be executing transactions, but all these shards would just like store data. And you would still have to like manage all of them and come to consensus on them, so we would always test things without actually having applications with user funds running into it. It'd be kind of like a big hard drive that's being controlled by proof of stake. And the idea was that, well, and this was phase 1, and then once we got that and it was secure and it was working, then we would like transform those hard drives into like computers and start running transactions in them. But at least it would kind of incrementally give us confidence that it worked. And this third part, this like transform the hard drive into computers, is always the most like nebulous part of the roadmap. In parallel to this, we started working on this. This concept of rollup came up, and rollups are basically separate Ethereum networks that run in parallel to the main chain and rely on the main network to get security from. And we could do like a whole panel on how they work and why they're secure, but they're basically a way for us to actually get what we wanted to get into this phase 2 through like a free market, if you may, like through applications building on Ethereum rather than through like protocol design. So as we were like building this thing, we started to see, oh, well, people are coming up with these rollups that might actually be a good way to scale Ethereum. And the neat thing is that these rollups actually produce a lot of data that they need to store on Ethereum. So this first idea that we had around like having a bunch more storage on the network was actually still quite valuable, because then instead of having the protocol use it directly, these rollup applications could use it. And it would also simplify things at the protocol level, because we would just have to keep track of one kind of Ethereum chain, and then the rollups could all hook into that, but that's not a concern that we have to like manage all of those rollups in the protocol directly. And so this was like kind of the second iteration of that. And then the last kind of insight which got us to the design we have today is that today the software that runs Ethereum as a proof of work chain does not only work with proof of work. So it runs proof of work on the Ethereum mainnet, but if you run like a test net or an enterprise network, it can use another consensus algorithm. And the software has been battle tested since basically Ethereum launched. We know it's secure, we know the applications run in it. So we had this idea, well, what if instead of kind of moving everything to the new system, we simply have the old system stop listening to proof of work and listen to proof of stake. And we already knew that like it could listen to another type of consensus algorithm. We just had never tested like transitioning to another one. But this is roughly like the design that we ended up with, and that's what we've been testing for the past year. I guess, yeah. Any questions here? Yeah. Okay, that was the most like complex part. It should be downhill from here. So there's pictures now. So this is kind of what the system looks like after the merge on Ethereum. We have an Ethereum client is basically a node running on the network. So when people say it's like an Ethereum node, it's like a piece of software that runs on the network, verifies transaction. You can think of it like an instance of an internet browser. It's not like, it's like one browser that's open, if that makes sense. And so there's two parts to this client. So there's this beacon node, and our proof of stake chain is called the beacon chain, just to be clear. So this beacon node is the piece of software that runs the proof of stake chain, verifies that like who's the latest validator that should produce a block, did they produce a red block, did other people vote for that block, and so on. And so that's kind of doing all that stuff. And then we have what we now call like an execution engine or execution client, which is the current software that runs proof of work. And this is what actually verifies the transaction. So when there's a new Ethereum block, this thing like runs through every single transaction and makes sure that nobody is doing anything funky in them, and then just says whether it's valid or not. And we basically, with the merge, kind of combine these two things where we have the beacon node receive a block from the network, which now includes transactions, and then it shoots it down to the execution engine, and it asks it, can you run these transactions for me, make sure that they're correct, and then the execution engine can say yes or no. And this is really neat because it means that this beacon node part just keeps doing all the proof of stake stuff it's been doing, and then this execution part stops doing proof of work, but gets to do all the other stuff that it was doing before, and we know that the software works quite well. And yeah, we call this the engine API. It's just the way that like the beacon node asks the execution engine for stuff and then gets returned. And so basically post-merge, this is what like an Ethereum block looks like. I should maybe have the pre-merge one to show. But one way you can think about the blocks on the beacon chain right now is there's not this section. This is just empty. So the blocks on the beacon chain, slot is basically like the number of blocks in there. Like it keeps information about like, okay, where are we at? What was the previous block? What's the current state of the system? And then at the stations are vote on the beacon chains, so it keeps track of like who voted for what. Deposits are new people coming in, exits are people going out. So it just kind of keeps track of all this information, like who's voting for what are the new blocks, what's the latest stuff. But it doesn't actually produce transactions. Whereas right now, kind of on the proof of work chain, these blocks, they still have this amount of like this similar like metadata about like the state of the network, but most importantly, they contain a list of transactions, which is like when you send a transaction on Ethereum or Beiko. It's just one of those there. And so the idea with the merges, we just combine those two things. We kind of use most metadata for the proof of work blocks. So all the stuff that had to do with like the difficulty of mining and all that, we just set it all to 0 and ignore that. But we keep all the transaction-related stuff, and then we keep all the consensus-related stuff for proof of stake. And what's neat is like for applications and users of Ethereum, this means there's basically no changes to how Ethereum works. So the block times change a little bit by like 1 second, and they become really predictable, whereas proof of work they're kind of targeting an average and have really high variance. We set a bunch of stuff to 0 related to mining, and then there's one single kind of instruction in Ethereum's virtual machine that we change that used to take some data from the mining stuff and expose it. We just change that to expose something else, but it still works, doesn't break anything. And so for developers, it's just like your smart contract does not even know that this is happening and just keep working as it always did. I guess yeah, I'll pause here. Does that make sense? Yeah.
Are there any timing assumptions needed for proof of stake that were not needed for like time synchronization?
You mean at the protocol?
Yeah, do the nodes need to have a notion of time?
So the nodes on proof of work and proof of stake both have a notion of time. The protocol on proof of work, the protocol doesn't really care about time. It cares much more about block numbers. There's a couple like small rules, like if you have block A and block B is after, the time of block B can't be in the past relative to block A. But like we don't care if it's like 1 second or a year after. In proof of stake, I'm not like an expert on how it works, but I'm like 80% sure of this. I don't think the protocol itself makes assumptions about time, but because we know that everything happens every 12 seconds, the implementations of the protocol do make like assumptions about time, because they know that like every 12 seconds they should check for something. And because something happens every 12 seconds, like maybe 4 seconds in, we can check for something else. So like if you mess with time on proof of stake, stuff will break, but I think it's more the implementations that will break rather than the spec. But there might be things that would break in the spec, but I'm 80% confident it's not. But definitely it's more time aware than proof of work is. Proof of work basically doesn't care about the time. Yeah. And we saw this on some of the testing where like some clients on the proof of stake side, for example, if nothing had happened, in like a minute, they would move on because they assume something would happen every like 12 seconds. And whereas on the proof of work side, if nothing happens for a minute, it's like it's not frequent, but like it happens. So like clients were more resilient there, so we had to change some stuff in the implementations to make it not just like cut off after like waiting for a minute or something. So there's been some changes already because of that. But yeah, definitely more time sensitive.
You mentioned that in the execution layer, sometimes you have access to things like block hash or whatever difficulty and stuff like that. There is some other interfaces that you have. Are there newer interfaces that bring consensus information into the execution?
Yeah, no, that's a good question. So actually, the only thing we bring in is this pre-random value. We want to bring more data from the consensus layer in the execution because it's useful for smart contracts, but we just wanted to keep it simple, so we didn't do it now. But difficulty, so basically people use difficulty, which is like how hard it was to mine a block, as a source of like bad randomness on Ethereum. Because, and the reason I say it's bad randomness is because like miners can kind of mess with it, and like, you know, imagine you have like a lottery that depended on that. Miners could like try with a bunch of different difficulties and like only submit the block that was winning the lottery and stuff like that. So it's like, it's okay, you know, if your threat model is like lower than the block reward, which is about like 2 ether per block. So if you're using it for randomness for anything that's worth less than 2 ether, it's all right, but anything beyond that, it's not safe. But people do use it. And because with the transition, there's no more difficulty, it would be set to 0. And that would be even worse, right? It would go from being okay for some use cases to like just being broken. So instead what we do is there is this randomness value that we use to shuffle validators on proof of stake. So we just expose that and switch it. So that's the only information that's kind of neat there. And this is actually kind of neat because A, it does not break all the contracts, but B, it's also if you're a smart contract and you want to know whether proof of stake, like whether the transition to proof of stake has happened, you can just query this value, and because the value is formatted, the proof of stake value is like bigger than the difficulty value, you can know that if it's bigger than this, then you're in proof of stake. But that's the only information that's exposed. Any other questions? All right. So how do we like actually transition from one to the other? And this is like the really hard part, and I'll have a picture after to show it. But let me just like explain with words before and then walk through the picture. So again, in proof of work, we use difficulty to mine blocks. Every block has a specific difficulty that it adds to the chain, and if you sum all those difficulties together, you know, there's like 50 million blocks on Ethereum, so like you sum those 50 million values, you get what's called the total difficulty of the chain, which tells you like how much hash rate was put to mine this chain up to now. So what we do to trigger the transition is we set a total difficulty value that we want to like exceed, and we call this the terminal total difficulty. So once we hit this value, we basically tell the nodes on the network to stop listening to proof of work for more blocks and to instead start listening to proof of stake. And so yeah, once we see that value, we kind of determine that block to be the last proof of work block. And there might actually be like a couple candidate ones. So you can imagine, you know, 2 miners come up with a block at the same time. There might be like 2 or 3 kind of valid potential last blocks, but the children of those blocks are invalid. You really need to be the first one that crosses the boundary on a specific fork, but it's possible that like different miners find a solution at roughly the same time, so that the system can kind of handle that, and then just discard anything that would be mined beyond that. And so what happens then is the validator that's set to produce the next block on proof of stake basically just starts including transactions in their block and kind of references that last proof of work block and goes on. And then in proof of stake we have this concept of finality, which means like if you want to revert the chain prior to that point, you basically need to be willing to burn at least a third of the stake, which is what we were talking about earlier. So we consider that to be pretty final. It's like, you know, for all intents and purposes, unless you're like a nation state actor attacking the network, like no one's going to revert that. So that's like the thing we want to wait for. We want to wait for this first block post transition to be finalized, and then we know that like there's no way we can reorg back through that in normal network conditions. And so this whole process, like, you know, from like the first to the second, that could take like, you know, a couple weeks because we're just waiting for it to happen. But then once we hit this block, the next block comes instantaneously, like 12 seconds later, and this block gets finalized about 12 minutes later in normal network conditions. So like the whole transition takes like less than 15 minutes, and there's no downtime. We're just at a kind of period where we're waiting for it to be final, but in theory, like there should be nothing that happens during that time. So that's kind of neat. And so this is what it looks like a bit more visually. So at the top we have the current proof of work chain. At the bottom we have this beacon chain that's running. So this first block here, you know, they're both just running in parallel, kind of waiting for the transition to happen. On the proof of work side, like we saw earlier, you know, they have proof of work stuff, and then all this content related to transaction. Proof of stake side, they have all this proof of stake kind of metadata on the consensus with no transaction. You can imagine the second block that we see on the proof of work side. This is the one that would like exceed the TTD. So like this one was not high enough, this one is high, it exceeds it, we're like, okay, this is the final proof of work block. So again, in parallel to that, nothing happening special on the proof of stake side. But then the block right after, that gets produced by a validator. It includes the transactions that are waiting in the transaction pool. And then the block after that basically has no link back to proof of work. It's just like completely referencing blocks built on proof of stakes. And it takes about 64 blocks for that one to be finalized, and then we know the transition's complete. So that's how it works. Any questions on this?
It seems like this is a pretty complex process.
Yes.
Why not just like, decide this is the last block and switch on a client with that block? Is there some?
Yes, that's a great question. Like, why don't we just like pick it? And if we did that, we would have saved probably 6, maybe 12 months of development. Like it's really hard to get this to happen smoothly on top. It's just like who picks it, right? This idea of like Ethereum is, we don't want to rely on a central third party or trusted third party at any time. The other thing we really like on Ethereum is we don't want the chain to stop. Some other blockchains are like fine to like, pause the blockchain for a couple hours and do stuff on it. Ethereum and Bitcoin really don't like that. Like the chain just does not stop. And this is why, we have all these like weird things about like voting on people doing bad stuff and like taking their money away. And these are all incentives for people to come back online and get the chain continuing. So like, those are really the two things we optimize for, is like not having a single party kind of controlling the network and like never stopping. And this is kind of why you need to do it this way, because what you can do is you can tell in advance to everyone that this block is going to happen. You need to give them enough of a heads up so that like they update their software. And then all the nodes on the network kind of agree to that and transition based on that. So there is a level of like coordination, like we need to choose a block obviously, but this doesn't happen in the protocol. This is like humans picking this block, and then everybody who runs a node makes a decision, like, okay, I want to run this software or I don't. And if they don't run the software, that's fine. They just end up on their own different version of Ethereum. But yeah, this is basically why it's like we need to have something in the protocol that like all nodes kind of equally like bring in. That's not like decided by one node. And we need it to be like instant. We can't like, it would be much easier if like we decided, okay, at this point we like shut Ethereum down for a day and then we just restart it with like this software. But we don't want to do that, so it's hard.
So you just mentioned that you have to update the software, and then previously you mentioned that if your mining node is offline, you can be penalized.
Yes.
So is there a mechanism for handling a node being brought offline to update and not get penalized?
Yeah. Totally. So if you're just updating the software, by the way, the node does not require downtime for that. Right?
Okay.
So it's just.
So that'd be the answer. Thank you.
But that's like a bit of a strong. In practice, what happens, that might be good enough for you and me.
Yeah.
If you're like Coinbase, they don't just like upgrade their nodes. They don't like download the software, put it on everything. So we have a bunch of test networks for Ethereum that we run through this transition, and so they get to try this software on a different network. And then this is also why you give them 2 weeks before, because like they could download this thing and like it's broken, right? And it doesn't have to be broken because of this upgrade. You can imagine, some other developer put something in that breaks the software. So like having a couple weeks gives us the time to cancel the whole thing or to fix the issue if we found out it was broken. So like the node itself doesn't have to go online, but the humans need to make sure that like the software works. Yeah.
I see. Thank you.
So what could go wrong?
Yeah, that's a good question. I'm pretty optimistic at this point. Like maybe, do you mind asking me this again after I'm walking through all the testing we did? And I think it'll be easier to answer because we spent the past year trying to figure it out. Any other questions before we move on?
Yeah, suppose there are 3 TTD blocks,
Yep.
and these 3 blocks are seen by 1/3 of the network. So block TTD, particularly block 1 is seen by 1/3 of the network. Second block is seen over, and then when the first validate, the first proposal, when it proposes the block, the committee for that proposal is
doesn't see it, right?
Yeah, they don't agree to that is the
Yes.
TTD block.
Yeah, that's a great question. So like, what happens if there's like 3 TTD blocks? First of all, as long as it's valid, right? It's like it is the TTD. It's not a child of it. It's not breaking any protocol rules. The validator has like discretion over it, right? They can choose any of those 3 and be fine. you can imagine a scenario where like, well, yeah, like you're saying, the validator after didn't see that block. They're like, oh, wait, so they might actually pick another one. And what would that look is like a reorg on the execution chain, right? It's like if you had, you know, like instead of going from like the second to last to like the first, then you go from the second to last to the second candidate. And this is why we want to wait till finality. So like for 12 minutes, it's possible. You can imagine the absolute worst case scenario. There's 64 candidate blocks, and every validator just sees another one of them. So like for 12 minutes, we're like debating, okay, which one is like the right one. But then once it gets finalized, again, unless you're willing to convert a third of the stake, then you can't convert that block. And this is why we wait this amount of time. So yeah, there is 12 minutes, which is like one of the things that could go wrong is for 12 minutes we're like arguing over what's the last block. Which in practice is like very unlikely, but you could imagine something like there's not going to be 64, but like you could imagine there's like 3 or 4, and like, you know, we jump a couple times between those or whatnot, and so, you know, maybe it doesn't take us a whole 12 minutes, but it takes us like 8 minutes and to like resolve that, and then at that point everyone agrees and we just have to wait that it's finalized. But yeah, that's why we wait basically. Okay, so I'll walk through like, you know, since we have these specs to transition, like how do we get this live on Ethereum? And take a step back, like I was saying, in May of last year, we felt kind of ready to move to this new system. And so what we did is we had a 4-week like hackathon with some client implementer teams to just prototype like, would this system work after the merge? Like, not the whole transition and anything, but this idea that like, okay, you have a beacon chain that's sending data back down, getting this validated, and then getting a response back, like, does this even work? So they did that for 4 weeks, and they got it working, which was nice. So it gave us like some confidence that the design was sound. Obviously there were tons of bugs, so we spent the summer fixing that. And then in fall of last year, we got everyone together again, and we had like a week-long coding session to just try and get this transition done. Like, can we start a new network on proof of work, have it mine a couple blocks? Oh, I think that was the mic. Hello? Can you hear
That's the
me?
mic.
Yeah, I think I should. Maybe I just pressed one. Oh, yeah, okay. Sorry. Yeah, so in October 2021, we had a week-long thing where the whole goal was to launch a new network under proof of work, launch a new proof of stake chain, and get it to transition and not break on the other side. We got this done, everyone was very happy. And again, there were tons of bugs because we did it all in a week, so we spent the fall fixing that. And in December of last year, we launched this first testnet to the public, which was called the Kintsugi. And the idea there is we had a spec which we were like, call it like 90-95% happy with. We knew it was not perfect, but we wanted to get feedback from application developers and infrastructure providers about like, does this work? Does this like break your stuff? So we got some, we reached out to some early users and got them tested out. We ran a bunch of protocol tests on the network. This is where we found this thing we were talking about with regards to timing and the issues there. So like we did some fixes to that. All the infrastructure worked, the smart contracts worked, so that was good. And then in March of, yeah, I think it's, can you hear me off the mic?
We can hear you.
Okay.
Yeah, I think it might be battery now.
Oh yeah, battery, there's a battery sign.
Okay.
Die again in a couple minutes. Okay. So in March of this year, we fixed all these issues we had found with the spec, and we launched a new testnet called Kill, which was basically spec frozen. So saying like, this is how the protocol's going to work for the transition. And there we really started getting like all the infrastructure providers, all the big smart contracts to test on it, started spamming the network to make sure the nodes not only like worked, in the happy cases, but they would work under like high loads and whatnot, and have it, this is still up and we're still running tests on it. And then we also introduced like a new thing to our testing suites that we did not do before, which we call shadow forks. And the idea there is that we had this software with the spec ready, so we would run through the merge on networks using just like a small number of nodes, so like one from every client implementation. And we basically tell those nodes like, okay, the merge is going to happen. And from their perspective, like it happens and they run, they move to proof of stake. And what's nice is that you can keep replaying transactions that happen on the main Ethereum network on our little shadow fork for a couple of days to test with actual real world usage. And then sync new nodes to that to make sure things are still working post-merge. So we've been doing like 1 or 2 of these every week since March, and this is just a really good way to find bugs across the implementation in the transition. And one thing I'll mention on this, I should have a picture of this, is Ethereum is like written as a specification for which anyone can write an implementation of it. And the best like non-blockchain way to think about this is like a web browser. So like if you're using Safari versus Chrome versus like Firefox, you go to like twitter.com, they all open the same web page, and they're like following the same protocol to render like Twitter on your computer, but they're like different implementations, right? Different code bases. And Ethereum works the same way, and even more so, the beacon chain and the execution chain are both specified independently, and there's different implementations for each of them. So this means that not only do we need to get the specification correct, we need to get these implementations correct. And with this transition, because people need to run both, you need to get every pairwise combination working, right? And this is why like these shadow forks are very helpful, is because we can run every, there's 5 times 4 is 20 combinations. We can run the 20 potential combinations and highlight like, okay, there's an issue with like this implementation here because it's broken with all these 4 other ones. Or we can highlight like, oh, there's actually an issue between like just a specific pair, a specific combo. And this is like what we basically do every week since March, is we run through the merge of every possible software combination, find any issues, and fix those, try again next week. Yeah.
Can you shed some light on the slide diversity pieces? I think before.
Okay, yeah. Yeah. So yeah, why would we do that? That's a good question. That also has a bunch of complexity. And there's a few reasons why we do that. First is just we want the specification to be correct regardless of any implementation. And what this means is, I'll pick on Bitcoin a little bit. Bitcoin does not have this. Bitcoin has just like software that runs Bitcoin, and this software is a specification. And what this means is you can imagine a world where like there's a bug in this software and like it mints a billion Bitcoin. Then you're kind of you're stuck in this place where like you need to fix the software, but by the time you fix the software, get it fixed out to people and whatnot, there's already a lot of blocks that have passed on the network. Like I said earlier, Bitcoin and Ethereum, they don't want to stop the chain. So it's like, these billion Bitcoins will be mined, and then blocks happen, transactions keep settling, and then it's very hard to like go back in time and undo this bug because so much time has passed. It's a bit easier on Bitcoin than on Ethereum because the transactions are like easier to separate out. But Ethereum has like all these weird applications on it that are all interconnected, right? Like there's NFTs on Ethereum, but there's not just NFTs, because like people take their NFTs and then they put it in a DeFi product and they get a loan against it. They take that loan and they buy another NFT, and then they sell that other NFT to somebody to go and pay back their loan. So there's like all these weird financial activities. So you can imagine if we have a bug, that printed a billion Ether, and it happened 2 weeks ago, the amount of just like intricate like dependencies, we can't like undo that chain of events. Especially because also a lot of it goes off chain, right? Like you send some funds to Coinbase or Binance, you sell it back to dollars, and like you're gone. You buy a car with Ether, like you drive away. Like, so you want like these transactions to, you don't want it to be possible to go back and like change the whole history. And so having these different implementations means there's like one specification that we can all agree is correct, and then everybody needs to implement that. And so if there's a bug in one, you can just change to another implementation. Just like if you have a bug in Chrome, you can download Firefox and run Firefox instead. And this is, and if the validators on the network kind of run these different implementations, then they can kind of catch that as well. So you can imagine, again, there's a bug where somebody like prints a billion Ether. Well, if only like a subset of the network is running that, everybody else will look at that and they'll say, hey, actually that's not wrong, that's not right. They'll start penalizing the people running that software, which is kind of an incentive for them to go and figure out what's wrong, because like they're losing money, and then hopefully like come back and fix it. So yeah, that's why we do this. That's the other reason why it's so hard to do this. So like the two big complexities that we have is one, it has to happen instantly, no downtime. The second is like we need to have a spec that's implemented, and every single implementation needs to be correct, but every single pairwise combination also needs to be correct. If we didn't have those two things, got it done in 3 months, and I would be here talking about it. But this is kind of what's neat about Ethereum. It's like it's what makes Ethereum resilient to like these failures. And so yeah, we value it quite highly. So yeah, and this is the type of stuff we find in these tests in these shadow forks. It's like, you know, Beacon chain implementation A has some issue connecting to like the execution engine B, and like why is that? And we debug that and fix it, and hopefully the week after. And so we did those, and like I had mentioned earlier, we have these testnets that we use before going to the main Ethereum network, and this is kind of where we're at in the process right now. So this is already like the final steps in the deployment process. So we have 3 testnets that we run through. We've run through 2 of them already, and you know we haven't found any major issues with them. We found like some configuration issues, like basically operator error, but nothing in those that like cause us to think that we need to go back and like fix something fundamentally broken. We have the next testnet that's scheduled for August, and basically we kept this one last because there were 2 separate networks today. Gordy is a application layer testnet that's very popular, and Crater is a beacon chain testnet that's very popular. So we're combining the 2 together and running to like a merge there. And yeah, we kept it last because this is where like most infrastructure providers or even home stakers, they would run like a testnet instance on there, and so they can run through the entire setup before to make sure that things are good for mainnet. And they could have done this obviously 2 times installed before, but this is really like the most popular one, so we wanted to make sure it was basically as ready as possible before we went there. So this is scheduled somewhere between like August 6th and 12th, and the variance is because it's hard to figure out when this total difficulty value is hit. And then assuming this goes well, we would then schedule it for mainnet and have the transition happen. So this is really like the last kind of couple steps we need to do. Yeah.
Roughly, what's the ratio of transactions in your largest testnet to the mainnet?
Pretty low there, medium there. The ratio of transactions is not like the challenge for Ethereum. What we're much more bottlenecked by is what we call state size. State size is like the list of all of the people's addresses and all the smart contracts and all the data that's stored in these smart contracts. So even though there's like a bunch of transactions on Gordy and Crater, they tend to be like more simple transactions. So for example, if I have 10 Ether, I send you 1, and you already had some, the state doesn't change, well it changes but it doesn't grow, right? Because it's like you have an account, I have an account, we're just changing the numbers. And so this is why the shadow forks are actually quite useful, because the shadow forks, they go from like mainnet state, and they put the nodes in that pressure. But it's, yeah, even though the transaction numbers are comparable, and what we do on the testnets also, if they're low, we can just spam them, because the testnet Ether is free, we just like set up a machine and spam it with transactions. And that's useful, but it's extremely rare that we run into a bug because there's too many transactions. It's usually just because the database is too hard to manage.
I don't see Rinkeby. We use Rinkeby on our test net.
Rinkeby is being deprecated.
Yeah, so you didn't even have to test against it. Okay.
Yep. So and it's not going to run through the merge.
Okay.
So,
because it's the oldest.
Sorry?
Because it's like one of the oldest.
Yeah, exactly. Yeah. So yeah, it's not going to run through the merge basically. And Rockstead is also deprecated, by the way. We ran this through the merge for the first time because it was going to be deprecated, and we figured, well, if we break it, it's not the end of the world. But the Rockstead and Rinkeby are being deprecated. Yeah. And in terms of just shutting them down, though, so like they're not. Rinkeby's not running through the merge. Rockstead has, but won't get any more upgrades. Rockstead will probably be shut down like by the end of this year. Rinkeby's probably going to have like a year to go because there's a lot of people on it and for some reason struggle to migrate.
Okay.
But it's not going to be a perfect mapping of mainnet, right? Like so, it's like your stuff will still run there, but it won't be a good staging environment. If that makes sense.
Sure, and if you need to have a test net 9 months hence, you should be on an earlier period.
Yes. Yeah, Gordy Crater and Sequoia is a new one we launched to replace DoDam. And the difference is Gordy Crater has an open validator set, so anyone can test it as a validator, but that creates a bit more instability for like applications because it's testnet validators, people don't have an incentive to keep them up, and so it's a bit more flaky. Sequoia, the validators are permissioned, like they are on like Rinkeby, so that means that like the network is just not going to go down because it's a bunch of it's like client teams and infrastructure teams that run those. So yeah.
Thank you.
Any other questions? Okay. Yeah. Last thing I have just before more is around proof of stake lowering transaction fees. So it doesn't, short answer, so like proof of stake doesn't change the amount of data we can like have on Ethereum. We could have more on proof of work, have less on proof of stake. It really just changes how the nodes come to consensus about like what's the state of the chain and like how people can propose blocks in it. One other thing is this transition does not allow stakers right now to withdraw their stakes. So there's obviously people who have already deposited in our validators today, and unfortunately it's like a one-way process on Ethereum today. And we wanted to simplify this transition as much as possible because, as you see, it's already pretty complex. So the ability to then withdraw a validator is going to kind of be upgraded right after this. That said, one new thing for stakers is when you send a transaction on Ethereum, you pay a transaction fee. Some of that goes to the miners. After the merge, that part of the transaction fee goes to stakers, so they get like a boost in rewards then. Last thing, actually not last thing, another slide, but very important. There's no E2 token, like there's only a single Ether, and like if people like tell you that you need to do something to get an E2 token, they're probably trying to steal your money. Please, like, don't do that. Yeah, so like there's only like a single one, and people will create scams for this. And then yeah, I have two more misconceptions. So
Can I ask?
Sorry?
But you would expect the transaction fees to drop, right?
Why?
Well, because they are a problem in some ways, right? For some applications.
Oh, I mean, we want them, sure. Like, we're working on a bunch of other stuff to scale Ethereum, and this is rollups, which we briefly touched on. So, like, yeah, we're working on a bunch of other stuff to lower transaction fees, but the transition itself does not help there, right?
Okay.
Yeah. But yeah, we would like them to be lower, obviously. And yeah, two more important ones. So, like, we talked a lot about like stakers and validators, and they need to put up Ether to run a node as a validator. But you don't need this if you just want to run a node on the network. You need this if you want the right to potentially propose a block. Anyone can run a node on the network for free, and the thing that you do if you run a node, you're still verifying that every single transaction is correct, right? Like you don't need to put up capital to do that. So you can run the software for free on your computer, and you know every time there's a new block, it'll go through every transaction, make sure it's correct. If it's invalid, it'll tell you it's invalid, and like wait for the network to figure out what's happening. Yeah, those are two different things. So like if you put up stake and you run a validator, then you get to produce blocks, you get rewarded for that, and you get rewarded when you attest other people's blocks. But if you just want to run a node, that's totally free, and you still verify that every transaction is correct. And then similarly, there's this like misconception around proof of stake that validators can like change the protocol rules, but that's not true because every node, even the non-validators, validate the rules of the protocol on each block. And so that means, for example, if all the validators colluded to change the rules, all the other nodes would like see that and reject those blocks. And in practice, you can imagine like a cryptocurrency exchange, they run their own nodes. So like if they get like an invalid block sent from the validator, they would at least pause and figure out what's going on because they see there's like a disagreement there in the protocol. So the validators can't like come together and collude and change the rules of the network because that leads to basically everyone else noticing. And then again, yeah, there is no need to token. This would be a scam. So please be on the lookout. Yeah, that's all I have. Thank you very much, and happy to take more questions there.
In proof of work, there's two major leaks of value from the network for like electricity providers and hardware providers. So proof of stake is like more efficient. But now like the security of the chain is directly tied to the market cap of the chain. And you've talked about these like anti-fragility where like there's a certain number of times an attacker can attack the chain before then essentially becomes impossible because all the ether is concentrated in the